My name's Steve Blackburn, and I'm a researcher at Google and also at Australian National University, and it's my great pleasure to be chairing a session here. And the first speaker we have here is someone who I know fairly well. He's actually my PhD student. Kunal Sareen is going to talk. Kunal is a PhD student at the Australian National University, and he's been researching the behavior of garbage collections on mobile devices. And he's going to talk to us about how we deal with memory management on mobile devices. So, Kunal, over to you.
Cool.
We'll just let him get mic'd up, sorry.
Hello? Oh, cool. Yep.
All right, thank you, Kunal.
Sorry. All right, so yes, thank you, Steve. So this work was done in collaboration with Steve, Sara, and Lokesh. And Lokesh is the GC lead at the Android team. All right, so given the ubiquity of mobile devices in our day-to-day lives, a scene like this is sort of unsurprising, of course. And with billions of mobile devices in the world, one would imagine that there's a rich literature on understanding and improving their performance. But unfortunately, it seems like mobile devices are woefully understudied in performance and memory management literature. And that's not because memory management is a sort of solved problem on mobile devices. In fact, if anything, memory management is an important concern for mobile devices given their limited resources like battery life and RAM. So then what's the reason for this gap in the literature? So let's look at this question in the context of Android, the most popular mobile operating system. And so it turns out that there's a variety of factors. So for example, some of the challenges to sound performance analysis on Android are that the Android runtime primarily only maintains some production garbage collectors. So some simple baselines you need to calculate overheads, which we'll discuss later, they don't really exist. And given the highly multi-tenanted environment of a mobile device, we often have many apps running at the same time, all vying for the same set of resources. So it's actually difficult to define a sound experimental methodology. And also, realistic applications are hard to control, both from an automation perspective and a technical perspective, as we'll see later. And these are just some of the issues plaguing sound performance analysis on mobile devices. And you can imagine how a lack of a sound methodology can both be a cause and a consequence of this gap in the literature. So I'll quickly give a brief overview of the Android architecture and some key background knowledge required for the rest of the talk. Android is a multi-tiered architecture based on Linux kernel, but what we're interested in is the Android runtime, which runs all applications, essentially. So starting an app on Android is actually quite different from a standard Linux machine, and that's because Android has a special process called the zygote, from which all applications are actually forked. So let's say a user clicks on an app in the launcher. The launcher then asks the activity manager to start the application, which then asks the zygote to fork itself and specialize the application. So in this way, the zygote is actually the parent of all Android apps. And this allows the Android runtime to preload common libraries and classes into the zygote with twofold benefits. You get faster app startups, and you also reduce memory consumption due to the copy on write nature of the zygote. But this actually complicates performance analysis. Since all applications are forked in the zygote, they share the zygote starting parameters, which includes heap sizes, type of GC to use, etc. It's actually quite difficult, or it's actually not really easily possible to change the heap size of an application like you would do in Java by just changing the command line arguments. And these are only some of the issues we face while trying to come up with the sound performance methodology, or performance evaluation methodology on Android. So switching gears a bit, how do we even measure the cost of GC? Well, so in our work, we use this methodology described by Zishin, who is here somewhere? I don't know. Zishin and co. In this ISPAS 2022 paper called the ELBO methodology. And just to be on the same page, I'll quickly go over the key points of this methodology, but I would highly recommend checking this paper out if you haven't read it already. So a simple, straightforward approach of measuring GC cost is to just sort of demarcate the start and end of a GC, like we've done here in yellow, and measure the cost in between, where everything else is assumed to be the cost associated to the mutator. Unfortunately, we know that that reality is quite nuanced, and that's because some GC cost is hard to separate from the application, costs like allocations, read and write barriers, concurrent GC, etc. But the idea of the methodology is, what if we have a magic GC, which essentially has all the benefits of the best GC without all the associated GC cost? Well, in that case, then we could run the application using this magic GC and then measure its total cost, and then use its total cost to calculate the overheads of the rest of the different systems. Right? But unfortunately, we don't actually have this magic GC, so the idea of the methodology is to try and best approximate it. So, and a key requirement of this approximation is having simple baselines which have clearly attributable costs and very few hidden overheads. So I've essentially skipped over the detailed steps of how do we calculate this method, this approximation, but in the end we get something like this, where the regions shaded in red are considered to be the empirical lower bound on the cost of each of these different collectors. And the cool thing about this is that the methodology is both language and metric agnostic. We could have been doing this in Java and Python, and we could have been trying to measure walk log time, CPU cycles, power, etc. Solver has 4 key requirements. And the first one is we want to have the ability to cheaply and reliably gather key metrics like GC time, CPU cycles, etc. We also want to have a way to reliably and repeatedly measure workloads in order to increase statistical significance of results. And we want to have the ability to attribute cost explicitly to the GC itself. And like I mentioned before, we want to have a well-understood and simple baseline, which minimizes metered overhead as it helps better approximate the quote-unquote ideal GC. So I'll go over some of the major challenges we faced while benchmarking our applications, but in the interest of time, I'll only discuss these 2. So since all applications are forked in the zygote, they share the same heap size arguments that the zygote starts with. And this means that if we want to change the heap size for an application, we have to do it globally. And this may not even be possible if we, for example, if we set the heap size to something which is too small, then the device might not even boot. And this is unsatisfactory, of course, because GC being a time-space trade-off, we really want to be able to control space in order to see what happens to time as we vary space. So what we do is we hijack the application specialization process to set the heap limits. And so after an application is forked from the zygote, it actually has to set up many things before the application can even start. So we insert a check here to make the application consult a metadata file, which essentially lists heap sizes for target applications. And if this application finds itself in the list, then it'll set the heap size to what has been specified in the file. Otherwise, it'll just do whatever the default is. And so this allows us to target specific applications without affecting the rest of the system. And since we can update the entries of this file at runtime, we can choose to target any application with any heap size at any time without recompiling or rebooting the system. So one of the most difficult challenges we faced was the tendency of our applications to introspect their own heap usage. And they do this for a variety of reasons, such as they want to resize software caches, or they want to preemptively call a GC before the heap is full, etc. But this is problematic for us because the benchmark is essentially dynamically altering its own behavior, and also it sort of breaks assumptions we have about having fixed workloads. And so in order to mitigate this, we intercept some standard Java APIs to return a false but consistent view of the heap back to the application. And this means that this should mean that the application's behavior is invariant to the actual heap size that it is running under. However, this is not a complete fix, as applications can still view their own heap usage, by using JNI or some other third-party library that we haven't mocked. And the best fix, of course, would be to edit the application source code to remove uses of this heap introspection. But unfortunately, this is not possible for the majority of Android applications since they're closed source in nature. So we also benchmark some standard Java workloads, so workloads on the phone. And for benchmarking these, we adapt some sort of standard state-of-the-art benchmarking methodologies from the server world. And we also for these benchmarks, we also further implement some simple baselines like no GC and optimize the existing semi-space implementation, like we'll see later. So now I'll talk about one of the other key contributions we have from our work, which is the curation of a benchmark suite consisting of real-world Android applications. So benchmarks are an incredibly important but often overlooked aspect of our field. And without such suites, we can often fall into the trap of using micro benchmarks or ad hoc benchmarks, which makes comparing performance across different studies quite difficult. And Android has many benchmarking suites, but most of them aim to test hardware or micro benchmark performance. And importantly, all of them are closed source. They don't use any real-world applications, and also they have opaque testing criteria. So in our work, we curate a set of Android benchmarks using real-world applications, and we make it publicly available. So since all Android applications are highly interactive, we need to be able to script user interactions in a deterministic and reliable way. So what we do is we use the UI Automator library, which is an open source library maintained by the Android team, to interact with UI elements. And this library was designed with black box testing in mind, which is great for us because we don't actually often have access to the source code for many of these real-world Android applications. It also allows us to be a bit clever. Like, for example, it allows us to wait for animations to complete, like waiting for a button to appear or disappear, instead of just doing fixed waits like we'd have to do otherwise. It also allows us to directly interact with UI elements instead of requiring the exact XY coordinates of a particular button or a text input, and also allows us to search for elements which are currently visible on the device screen. But this does come with some downsides, and that's because and now we actually have two ART instances running at the same time. And the first one is the application itself, like we're trying to measure, and the second one is the benchmark harness running UI Automator code that is essentially sending input events to the target application. And this is not ideal, of course, because we've increased the amount of variance in the system, but it's unfortunately the only way we were able to do this. So we curate a set of 10 popular real-world applications with realistic workloads over a diverse variety of use cases. However, we omit two notable use cases, web browsers and video games. Web browsers and similar applications would be predominantly JavaScript benchmarks with a very thin Android Java layer. And video games are much the same, as they often directly allocate into the native heap, or they use a game engine like Unity. So we faced many issues when trying to build this suite, but in the interest of time, I'll only go with this one. So benchmarking can still be quite flaky even when we're using UI Automator, and that's because dynamic content displayed by applications like Facebook and Twitter is actually quite problematic. And that is due to different layouts can actually have different allocation behavior or benchmark characteristics. And what I mean by that is, for example, you can consider something here like we have here on the left, which has a series of videos together. You can imagine that this is doing more allocations than something what we have here on the right, which is just a sequence of static images. And I'll show some results later which sort of corroborate this. So like I said before, we also use some standard Java workloads, and we benchmark them. So we use a subset of the Da Capo 912 benchmarks, and we also use GC bench, which is just a simple micro benchmark. And obviously, this is not realistic in a sort of mobile setting, but this allows for comparisons to similar studies to OpenJDK, and also allows us to understand core garbage collection performance. So we use two different devices in our experiments, but for the rest of this talk, we're only going to be discussing the Pixel 7 Pro results. And this is a picture of the actual experimental setup, which is sitting back on my desk in Australia. So I'm not going to go over the entire experimental methodology, but the key idea was that we tried to remove and reduce as many sources of noise as was possible. And I would recommend checking our paper out to see what other stuff we had to do. So these are the results for the vanilla Java benchmarks, but in the interest of time, I'll only go with this one. And so first, let me explain how do we interpret the graph here. So on the x-axis, we have the multiple of the minimum heap size for this particular benchmark. In this case, 1 is 18 megabytes, and 6 is 108 megabytes. And on the y-axis here, in this case, we have the task clock overhead. And the closer you are to 1.0, the closer you are to the approximation of the ideal GC. So this graph is actually quite interesting. As you can see, that our semi-space implementation, optimized semi-space implementation in light blue actually performs much better than the stock one. But what's also interesting is how the concurrent copying collector performs much better at smaller heap sizes than at larger ones. And we find that this is because it actually reduces cache misses due to more frequent GCs for smaller heap sizes. So now these are the results for the Android applications. And what we've done here is we've taken the geometric mean of the task clock overhead, in this case, across all the different benchmarks, excluding Twitter. And these results are sort of unsurprising because we can see that for smaller heap sizes, the two concurrent collectors actually have higher overheads. But what's also interesting is how the semi-space collectors have similar overheads to the concurrent copying collector at larger heap sizes. So now these are results for two of the Android benchmarks. On the left here, we have Airbnb, which sort of behaves like you would expect with smaller heap sizes having larger overheads and so on and so forth. Right? So you get this nice curve. But over here on the right, we have Twitter, which sort of behaves very chaotically, and there's no sort of visible trend here. And we believe this is because that Twitter is actually quite sensitive to the layout of posts, which are currently visible in the timeline. And you can see that each point actually has the error bars actually quite tight, suggesting that the results are quite reproducible within a particular heap size, but they're not quite stable across the entire range of heap sizes. And we believe this is because that each points are actually measured in different moments in time, so a different set of posts is currently visible in the timeline. So these sort of Twitter results underscore how difficult it is to come up with the sound performance methodology for, yeah?
Oh, sorry to ask a clarifying question.
Yeah. Okay. Sure. Sorry. These sort of Twitter results underscore the difficulty in trying to come up with a sound performance methodology using realistic applications with realistic workloads on a mobile setting. Okay. So in conclusion, we've identified challenges and pitfalls to sound performance analysis on Android, and we've also outlined a small benchmarking suite consisting of real-world Android applications with realistic workloads. And we also find that for a modest heap size, production RGCs have lower bound overheads of around 2 to 51%. All right, thank you.
Great. We do have time for a couple of quick questions.
You made some comments about dynamic content, and I guess what really confused me was scrolling through Twitter, we're seeing different posts on every single time we run the benchmark. Are we doing recorded replay of the server-side traffic to pin that between mobile runs or anything like that?
Right. So yeah. So there's a whole bunch of stuff I had to cut out from the talk in the interest of time. But essentially, what we're doing is we try to limit network traffic in a bunch of ways. And one way we do it, we limit the set of posts, the set of accounts which we follow, right? So we then only go to the followed feed, and then, for example, you would only theoretically you should only see chronological updates to that timeline.
Got it. But this benchmark is using real live internet content. So
Yes.
You
Yeah.
run it all at once before things change too much.
Yeah, and so yes, exactly.
Okay.
Any other questions? Yep.
Can you please use the mic? Thanks.
Which slide, sorry?
The very first slide, the results.
Oh, very first slide, the results.
Yeah.
This one?
Yeah. Why is that orange color going up with the increase in heap size?
So like I mentioned before, you mean this one, right? Yeah, so like I mentioned before, it's because we find that this, over here, you're actually reducing the number of cache misses due to increased GCs for smaller heap sizes. So you actually have better cache utilization, right? Which is an interesting result, right? You would expect smaller heap sizes to have larger overheads.
Since you're already on that slide, can you also clarify why the yellow line starts at me?
Okay. Right. Okay. So this is no. This is essentially an artifact of how Android essentially considers what is heap size. So, like in a normal runtime like Java, whatever you set on the command line, like XMS and XMX, that's the entire memory is available to the collector. So like a semi-space, you would actually only have half of that as from space and half of that as to space, right? But in Android, whatever you set as the command line argument essentially is just the from space, right? It's just the to space, and the from space is quote unquote free, right? So that's why the two copying collectors, the concurrent copying and the semi-space, we've shifted them to the right by 2. But the concurrent mark compact collector, which is just like a simple concurrent, it's not simple, but it's essentially a concurrent mark compact collector, so it only has the 2 space, right? So it's an artifact of how art deals with memory. All right.
All right. Well, thank you very much,
Thank
Kunal.
you.